Welcome to this lecture on separating in stages. There is no design recipe that works for all unit operations, but the ingredients are always the same. Typically, you first set up mass balance for the unit operation and for its individual phases in terms of flow sizes and composition. Then you introduce the equilibrium distribution of components between the different phases to determine how many equilibrium stages are needed for the desired separation. Hydrodynamics determine how close we might get to equilibrium within the physical constraints such as feasible pressure drop and flow resistance. Then, required equipment dimensions can be determined, or they are input data if available equipment is to be used. Finally, energy balances are needed to determine the required energy input. In this lecture, we will use items 1 and 2. Let me demonstrate that by the example of producing coffee. Suppose that you are asked to prepare coffee from ground coffee beans at a huge ceremony, the opening of a new center on sustainable bioproduction. Your product should be good coffee and in large volumes. Waste production should be minimized. For now, we focus on getting as much coffee with the right aroma concentration after extraction of the beans and neglect aspects such as caffeine content and energy efficiency. So let's have a look at the process of aroma extraction from coffee beans into hot water, the auxiliary phase. As aroma, compound 1A, is extracted from the coffee beans, the concentration of aroma in the beans decreases. Meanwhile, the concentration of aroma in water increases. This stops when equilibrium is reached, at which point the ratio of aroma in water and beans is given by the partition coefficient Ka of aroma between hot water and beans. When choosing the right ratio of beans and hot water and sufficient time for extraction, the extract can be served as coffee. At equilibrium, aroma in the hot water has mass fraction Ya, and in beans Xa remains. Now let's go to a sustainability question. If making good coffee corresponds to 1 spoon of ground beans per cup of hot water, can we still make good coffee from the exhaust beans from, say, the first 10 cups of coffee that you have made? Think for a moment. To answer this question, we consider the mass m of beans and of hot water that we equilibrate, with the concentration of aroma components X in the beans and Y in the coffee after one equilibration step, stage 1, and after a second equilibration step of the used coffee beans and fresh hot water, stage 2. This is determined by the distribution or partition coefficient K. For Y2 to be equal to Y1, we need X2 to be equal to X1. But since we extract aroma, X2 becomes smaller than X1, so Y2 becomes smaller than Y1. That implies dilute coffee with less taste, no matter how little hot water we add in stage 2. To understand better where the aroma, so compound A, is going, we can use the equilibrium equations in the mass balance per extraction stage. That we can solve, and it gives us the same form of equation in each stage. It tells us for each extraction stage the fraction of aroma that stays in the beans and may be lost. For example, Xa1 over Xa0 for stage 1. This fraction depends on the amounts of beans and hot water in this stage and the partition coefficient. Now we have a mathematical translation of coffee extraction. What we see in these equations is an important group, the ratio Me over Mb of the amount of hot water and beans, times the distribution coefficient K. This term is called the separation factor S, and it is an indicator of how well a process stage works. You will encounter this separation factor for many types of separations. But still, we do not know how to prevent that aroma goes to waste. Instead of contacting fresh hot water with fresh beans, we can also contact fresh water first with partly extracted beans, where it extracts remainders of aroma. Then dilute coffee stream flows onto the first stage, where it encounters the fresh beans that are still full of aroma. Much more of the aroma is extracted in this way, meaning that our feedstock is used much better and less is wasted. This concept becomes even more interesting when we perform the mass balance calculations and evaluate economics and sustainability. Now we move from batch-wise coffee extraction to continuous extraction, so we can also scale up easily. The concept is the same for liquid extraction. Our formulas will not really change. For separation factor S, we just take flow ratios instead of mass ratios. The auxiliary phase, now called V, is kept on top in the equations of the feed phase, now called L. If a solute I has entered an equilibrium stage with feed phase L, and maybe also with auxiliary phase V, how much of it leaves with L phase and how much with V phase? The mass flow of I leaving with auxiliary phase will be FV times YI. The mass flow of I leaving with feed phase will be FL times XI. The ratio between these flows of I is the separation factor that we just learned about. So a compound's separation factor can tell which proportion of the compound goes in which direction. If the separation factor is larger than 1, component I mostly leaves with the phase V. If S is smaller than 1, most remains in phase L. This is useful for designing a countercurrent separation. To know how much will be extracted and how much not, let's start from the end. The mass flow of compound I leaving stage 2 with L phase is FL times X2. Then we know that S times as much will be leaving with the V phase. We can sum these two leaving streams to see what has been entering stage 2 with L phase. So that's also what leaves stage 1 with L phase. Then S times as much leaves stage 1 with V phase. Knowing the two outflows of stage 1 and one of its inflows, the mass balance of stage 1 tells us how we also can express its second inflow in terms of FL times X2. Comparing how much enters and leaves overall at the L side, we get an equation of the fraction that is not removed from the feed. The final equation was shown some slides earlier. Now you know how it can be derived. When adding stages, more terms must be added into the equation, and this leads to the so-called Kramser equation. A plot of the Kramser equation shows that we can extract everything if we have sufficient countercurrent stages and if the separation factor is larger than 1. A larger separation factor is achieved by choosing an auxiliary phase with a high K value due to high affinity for the compound to be removed, or by using more of this phase. More stages and more auxiliary phase also lead to more costs, and an economic assessment can tell if they are worth the extra product extracted. Countercurrent staging can be further elaborated. By coupling different multi-stage units with intermediate feed stream, one can separate different components not only from the feed solvent but also from each other. Such an example is shown here. A mixture containing compounds A and B is fed between so-called top and bottom sections. A moves up and B moves down. Besides extraction, many other separations can exploit a stage-wide equilibration of two phases. The approach is very, very general. Later it will also be used in the PDO case. Of course, actual equipment needing for achieving stage-wise contacting will look very different for each system. Discussing such aspects is more than we can do in this MOOC, but we can have a better look at some of the more important types of separations. For that, see you in the next lecture.